Then we have to discuss how to find the focal length of a concave lens, right? So let's see that. Right. So this is first you have to understand the nature of images formed by a concave lens, right? So let's say focus, primary focus here, secondary focus here for the concave lens. Then if you place an object, what happens? You can draw a light ray, and then light ray gets diverged, since it's a parallel, then as if it goes through the, it's coming from the primary focus, right? So those are explained in the theories. Then another light ray, you can draw it, which goes through the center of the lens, and it doesn't get any deviation, just goes straight through the center. So the meeting point of these two rays, it creates a virtual image. No matter the position of the object, this is the object, this is the image, no matter the position of the object, you can always see the image is formed only between the center of lens and the focus. Got it? Center of the lens and the focus. Always it only forms at center of the lens and the focus. And it is always going to be non-inverted and small non-inverting, like that. So you need to locate the position of this image. The position of this image, you need to locate that. So how are we going to do that? Right? So you can see this is the principal axis. This is the principal axis. So the tips of these should be on the principal axis, right? Like this. Okay. So to do this, the experimental setup is somewhat different here, right? Experimental setup. Actually, the previous method used in you cannot just place an optical pin here. Do you understand? To locate this, if you place the optical pin here, then the image of that optical pin is also going to be made by this lens. So for this one, you can use a thicker object pin. Then you will see the image of the both object pin and the optical pin through the lens. But that is not, so the using the parallax method is going to be very hard in that case, right? So we are going to go for a new experimental setup, which is more convenient than using that method, previous methods, right? Okay. So for this, you are going to use the object pin. This is the object pin, like this. You hang the object pin onto the principal axis using a stand. You're not going to place it like this. You will understand why that is, right? You're not going to place it like this. You're going to place it like upside down for the object pin. Okay. You will understand why that is once I draw the experimental setup, right? Okay. So since we know that the images are going to form only between focus and the lens. Actually, we don't need to find the focal length approximately as well, unlike in the previous one, right? Okay. So here, so this is the mount. Then you place the concave lens here. Place the concave lens here. Then let's say this is the principal axis, right? Position P. Then what do? You place the object pin like this. Get it? You will understand why. You place the object pin like this. So this is pin 1, right? So it is hanging. It is placed like this, right? So now what's going to happen? Let's say focus is somewhere here. The image of this object, a small image of this object, is going to be formed between focus and the lens. So we need to detect the position of this image. Position of the image. To find that, you cannot place optical pin here, right? Cannot use the optical pin here because the image of this optical pin also will be formed. So you are seeing two images from this side, right? So from this side you are going to see two images. So it is going to be confusing, right? So in this way, so to detect the position of this image, you place a mirror like this at a known distance, let's say like 4 centimeters. So you place the mirror at a measured distance. Then the second optical pin or the observing pin, you place it like this. You place that like that, right? Then when you look through here, this is what you are going to see. Sorry, the mirror is not this high, right? Only a half of the lens is covered by the mirror. Okay, only a half. So this is observing pin, pin 2. So what you are going to see is, you are going to see half of the mirror. Let's say this part is the half, and below that, the part of this part of the mirror, right? So through the mirror, you will see an image of this pin 2 at an equal distance, right? Let's say this is distance x. So at an equal distance from x to this side, you see the image of pin 2. So let's say it is formed right here. It is actually not formed right here, right? You have to use parallax method to exactly put that image here. Let's say it is made here. So this is the, so through the mirror, what you see is image of this image. So let's say that image is like this. You see that. Then what do you see? Through the lens, you see this image. Through the lens, you see this small image like this. Okay. So using parallax method, you can position exactly, you can change this distance till the image caused by the mirror coincides with the image. So you will see no relative motion between these two images. So the one image is through the lens, other image is through the mirror. So you are coinciding those two images using the parallax method, right? So you can understand that this distance also is x, right? So from the mirror, the image is formed at a equal distance. So if this is x, this also is x, right? Then what is, so the object distance is from the lens to the object, so that is u, from the lens to the object, u. Then the image distance, this much, that is v, from lens to the image. You can measure that, right? So what is that v? So this v is, as you can see, x minus y. This distance x minus y is the image distance. So y is a known value. You can simply measure that value using the. Then x also you can measure, right? Once you find the position of the pin 2, you can find the x. So x minus y is going to be the image distance, and you already know that u. Okay? Then, so similarly, you have to get about 6 positions of object distances and 6 positions of image distances in order to draw the graph, right? Okay. Then just apply the lens equation. So here 1 times 1 over u plus 1 over f, right? So here as well you didn't apply sign convention. So for v values you only get positive values, right? You only get positive values. So you can see this is y equals mx plus c. So for u and v, u values are positive obviously, already positive. And v also are positive because all the images formed, they are virtual images, right? All the images are formed for any location of the object, only virtual images are formed. So v also is positive. So then consider 1 over v, 1 over u, 1 over v. Then you get the same values, not the same values, I mean reciprocals, but the same sign. Then you can simply draw the graph. So 1 over v, 1 over u. So y equals mx plus c, right? Positive gradient. This also must have 45 degrees, okay? Then from the intercept, you can find 1 over f. So that gives you the focal length of the concave lens. So that's the procedure there, right? You can take this down. Write down these points. A concave lens, write down this under their discussion, okay? A concave lens forms all its images between the lens and focus, for real objects, to the same line, right? To get well spread values, for v means image distance, right? To get for v, comma, u values also should be well spread. U values also should be well spread. right? So for these v values, those are limited only between FN lengths, right? So to get well spread values for v, it is important in this part especially. So for that, these object distances, you have to use object distances. The values of object distances should be well spread, right? In order to get these v values, well spread v values. Otherwise, when you are drawing the graph, that graph the coordinates should be limited to a very small location, right? Small area. So to prevent that, you need to get well spread u values here, especially here. Right, second point. When reading intercept from the graph, the value of intercept could not be very accurate, So to get a more accurate value for intercept, follow the method below. Okay, so this is the method. I'll explain that. This is applicable for the first part as well, for the convex lens as well, for any experiment when you are doing the intercept, right? The problem here is, so you have this one. You don't know the exact value here, right? When you're finding the intercept, you cannot read the exact value here if it is like this, because it doesn't go through right here like this. If it doesn't go like that, you don't know the exact value here. So to find that exact value, you go for this one, this graph. So let's say you have a clear coordinate here. Then you know the values of x and y. You can substitute x and y values, right? Then this m value also you can find using the graph. Using two coordinates, you can find m, right? So if you know these three values, you just substitute a one coordinate here and the gradient. Then you can find intercept. So this is a more scientific method to find the intercept accurately, right? Okay, below that, right? Find the gradient and substitute a coordinate in y equals mx plus c, in order to find the intercept, more accurately, right? Okay, so this that one you can apply that for any experiment whenever you have to find intercept, right? But if they especially ask that, right, you can always go for that. If that doesn't it actually intercepts the y-axis through a known value, right? If it is not certain, you can always use this method to find the intercept.